think we're now ready to start talking about some general trends in the periodic table. And the first one that normally comes up in a lot of first-year chemistry classes, and it even shows up on some chemistry standardized tests, is the notion of ionization energy. Ionization energy. And what this is essentially the energy required to remove an electron from the state, the neutral version of that atom. So let's say it's the energy to remove an electron. And just in case you haven't been exposed to the idea of what an ion is, I guess this is a good time to explain it, and then this will make sense. So an ion is essentially any atom or molecule, and we'll talk about molecules. Molecules are just combinations or groups of atoms that are all bonded together in some way, and we'll talk about bonding in a few videos from now. But it's an atom or a molecule in which the protons don't equal the electrons. And if the protons don't equal the electrons, then you have some charge. If you have more protons than electrons, you have a positive charge, right? So let's say if you have hydrogen, normally it's neutral, right? It has no charge. But let's say you were to remove an electron from it. So now you have hydrogen plus an electron. Hydrogen only has one electron outside, so now it just has a proton on the inside, no electrons on the outside, so now it has a +1 charge. Right? We could write a -1 there. And now what we have done in this, I guess we could say this procedure or this reaction, is we've ionized hydrogen, we've removed an electron. And in this case, this type of ion that hydrogen is, where your protons are greater than your electrons, and this is just a nice word to know, this is called a cation. A cation is an ion with a positive charge. Now you just as easily could have a situation where you have a, let's say, I don't know, let me take an element. Let's say we start with chlorine. Cl, right? In a stable form, it has 7 valence electrons. And why don't we add an electron to it? And now it'll be Cl. And now this will actually be pretty stable. It'll have 8 valence electrons, but it'll have a negative charge. So this right here, this is a negative ion, and that's known as an anion. Anion. The way I remember it is, I don't know, in a lot of words, A means the opposite or negation, right? The A prefix. So anion means a negative ion. And then obviously cation is the other. But ionization energy, it really should maybe be called cationization energy, because it's the energy required to remove an electron, not remove or add an electron. So it's really the energy required to turn something into a cation. So we've already discussed the periodic table, and we'll get to this chart in a second. But just based on what we already know, which elements will it be harder to remove an electron from, and which ones will it be easier? Well, we already talked about, let's start with group 1, just because it is group 1. Group 1's right here. And we'll start especially with the alkali metals. We can put hydrogen aside for now. But all of these guys we've talked about a lot. In order for them to get to the magic number 8 in their outermost shell, the easiest way for them to do it is just to get rid of that 1 valence electron they have in their outermost shell. So this, let's say potassium right there. Potassium has 1 valence electron in its 4th shell. If it just got rid of it, then it has 8 in its 3rd shell. Then it looks a lot like argon from an electron configuration point of view, which would be nice. So these guys really want to give away electrons. So it requires very little energy to ionize them, or to cationize them, to take away their electrons. So this is low ionization energy. Low. And I think you see where this is going. What about these guys? Well, what about neon? How hard is it to remove an electron from neon? Well, neon is completely satisfied. It doesn't want to even deal with any of this reaction business and bonding business. It's like, you know what? I've achieved happiness in life. Don't mess with my electrons. So it really doesn't want to give away its electrons. Neon or krypton or argon or any of these noble gases. So to remove an electron from one of these guys requires a lot of energy. So this is a high ionization energy. So in general, as you go from left to right across the periodic table, it goes from low to high. And some people, they memorize this, but you really don't have to memorize it. You just say, look, these guys have one extra electron that they're always trying to get rid of. These guys has two, so it requires ideally they'd want to get rid of maybe both of their electrons, but the first electron doesn't want to jump off as much as the first electron here, because the first electron here, you get rid of it, you immediately get to the super stable state. And that trend just becomes more and more true. This guy definitely, under no circumstances, wants to give away an electron. This guy's so close to being like neon that he definitely doesn't want to go a step backwards and look more like oxygen. So he doesn't want to get rid of an electron. So the trend is pretty clear. Anytime you're confused about the trends, just look at the extreme cases. This guy wants to give away electrons. This guy wants to get electrons. So if you say, what's the energy required to take it away electron? Well, this guy is almost going to give it to you. While this guy is going to be very hard, especially neon, to take away an electron. Now what happens as you go down? As you go down in this direction, let's say you go along a group, right? We already established that these alkali metals, they'd like to give away electrons. But as you go down, the electron cloud gets bigger and bigger. And you could say this 55th electron, there's 55th protons. There's also in a neutral cesium atom, there's also 55 electrons. That 55th electron is a lot further away from the nucleus of this atom than the third electron is in the case of lithium. So the 55th electron, not only does it want to be given away, but it has even a weaker attraction to the nucleus than the third electron does have in lithium. So because you're getting larger and larger as you go down a group, and the electrons are getting further and further away from the nucleus, this guy wants to give away his electrons even more than lithium does, right? So ionization energy decreases as you go down. Even though xenon really wants to keep his electrons, he's a little bit more willing to give them away than neon is, right? So in general, this is activate the ionization energy, or the energy required to ionize an atom. It will increase as you go up. Right? And if you ever forget it, don't memorize these things, because that might be useful for just one test. But then later in life, when you're 42 and someone asks you, hey, what has a higher ionization energy, cesium or fluorine, you might have forgotten it. But then if you look at a periodic table, you'd say, oh, cesium, it has this one electron that is just dying to give away. It's super far away from the nucleus. That 55th electron just really wants to leave. While fluorine, that ninth electron is, it just needs one more electron to become, let's say neon. Neon is super happy. All the electrons are in the stable configuration. They're close to the nucleus. There's a lot of attraction with the protons in the nucleus. They definitely don't want to give away their electrons. So if you talk about the energy required to remove them, very low energy at cesium, very high energy at helium. So that's the trend. And this is just, this trend we'll see often. This is this is your willingness to give electrons, and this is how much you want to hog electrons or keep them to yourself. And this right here, this is actually, I got this off of Wikipedia. This is actually the actual measured ionization energies. And people looked at patterns like this. I'm not sure if they actually looked at the ionization energy, but they looked at patterns like this. And this is actually where they came up with the periodic table, because they said, look, as we increment up the number of protons that we have in an atom, and likewise the number of electrons, we see these repeated patterns, or these periods in the elements. So this is hydrogen. So hydrogen's ionization energy is around 13.5 electron volts, right? Which is a unit of energy. It can be converted into joules if you like. But then all of a sudden, helium's a lot more stable. It takes almost double the energy to remove that second electron from helium, because it's so stable. But as soon as you do that, as soon as you go from helium, this point right here, that point right here is lithium, right? Lithium is atomic number of 3. Let me put that in this is lithium. All of a sudden, to remove an electron from lithium, it only requires 5 electron volts. So less than half of what it required for hydrogen. And then as you go to the right of the periodic table, the ionization energy keeps increasing. I mean, these little divots are interesting. We could talk about that maybe in a future video. But then the ionization energy increases all the way to neon. And then you get to neon, and then you add one more. See, neon is the noble gas. It's completely happy. Then you add one more electron, you get to sodium. And you say, oh, well, now sodium, it's really easy to take away that electron. And the ionization energy drops. And not only did it drop, but here it dropped slightly below lithium. So you see this general trend. So these are the noble gases right here. Let me make sure you can see them all in the video screen. Helium, very hard to remove that 8th electron. Neon, it's very hard, but a little easier than helium. And that's because neon's a little bit bigger. The electrons are a little bit further away from the nucleus. Argon, same pattern, but it's actually interesting. Argon is actually not that different than hydrogen. Now, krypton, same thing. It's hard to remove that electron, but it's actually no harder to remove the electron on krypton than on hydrogen. And then xenon, and you go all the way out to radon. As you can see, why is the distance between these increasing? Well, if you remember the periodic table, xenon and all of a sudden when you go after argon, then you have all of the D block elements that go in. So after you get to argon, so notice this is where you only had S and P block elements, Now all of a sudden the D block elements show up, so you have more subshells to fill up. And now all of a sudden, you're starting, before you get to radon, you're starting to fill out the F block too. And that's why that distance is increasing, because you have to also fill out the F elements. But the general trends that we just discussed, they apply here, that as you go to the right along a periodic table, it becomes harder and harder to remove an electron, because everyone wants to get to the magic number 8, and it's very hard to remove them from a noble gas. But then as you go one more above that, this guy would love to give away his electron and get back to a configuration like neon. And then the other trend is as you go down a group, in this case, these are the noble gases, the ionization energy decreases, and that's because just the overall radius of the atom increases, so the valence electrons in radon are a little bit less strongly attracted than the valence electrons in helium. Anyway, I think that's it for ionization energy. I'll continue this in another video. We'll talk about metallic character and electronegativity.